This is lesson 2.6, proofs using definitions that we already know. We've actually done some of this previously in our first unit when we were learning about the angle addition postulate and other things, and we had our initial intro to proofs packet. In chapter 2, section 2.5 of your textbook, there are properties of equality listed in a table. And those are the properties of equality we used to do some algebra proofs in a previous unit. Now that we're diving into these real proofs, I'd like you to take the moment, pause the video, see if you can write these as a proof. So we have statements on the left and reasons on the right. Take a second to see if you can get these. For number 1, the first step would be to add 8 to both sides. So line 2 of your proof would be 4m equals negative 4. The first line in this case is the given equation. The second line, to get there, we added 8 to both sides, so we used the addition property of equality. The next step to solve for m is to divide by 4, so m would equal negative 1. To get from line 2, from equation in line 2 to the equation in line 3, we divided by 4, so we used the division property of equality. For number 2, our first line is our given information. It's our given equation because we don't have a picture or any geometry context to set up this problem. They just gave us an equation. To solve this, the first thing I'm going to do is multiply by 6 on both sides. So I have z minus 5 equals negative 12. For some of you, you're going to want to show your steps in between each line of your proof so you don't make any errors by doing it in your head. To get from line 1 to line 2, we multiplied by 6, so it is the multiplication property of equality. And now I'm going to add 5, so z equals negative 7. Since I added 5, the reason would be the addition property of equality. Remember, the only one we don't want to abbreviate is subtraction because we don't want to confuse it for substitution. Now that we're getting into proofs, it's time for us to define proof. A proof is an argument that uses logic, definitions, properties, and previously proven statements to show a conclusion is true. So based on this sentence, you need to think back to lesson 2.3. Are proofs based on inductive or deductive reasoning? They're based on logic, definitions, properties, and previously proven statements. This is based on deductive reasoning. Our proofs are deductive in nature. When we explore concepts in class and you're drawing conclusions, that's inductive reasoning that you're learning, much like you did in middle school. When we're doing formal proofs, making formal arguments, we need to use deductive reasoning, which is why it's really critical for you to know your vocabulary and how to use it to make your arguments and to explain your reasoning. Justifications are shown that every step, to make sure that every step is valid. Now we have two different things in geometry. We have postulates and we have theorems. I've mentioned this before, but we haven't talked about them in great detail. Postulates are things that we are assumed to be true without formal proof. They're things that Euclid could not prove using definitions and properties and key facts. They were things like 2 points make a line. He could only draw examples and say, hey, do we all agree on this? We think this works for every case. We've explored it a lot. We do. We have no formal way to prove it. Therefore, it became a postulate. It's not just something that we're like, oh, that's hard. I don't feel like proving it, so I'm going to call it a postulate. They're things that we really need to start from a fundamental place, from a beginning point, and we just find something that we know and that everyone agrees is absolutely true, even though there's no way to prove it other than inductive reasoning, and then we call it a postulate. And based on those postulates and other definitions and properties, we can prove bigger theorems that might be related to it. Theorems are conditional statements that we can prove. What's the difference between them? Both are written as conditional statements, or can be written as conditional statements. I'm just going to write as conditionals. Both can be written as conditional statements. Both are used in proofs. Yes, you can use a theorem in other proofs as long as it's something that you've previously proven. Theorems must be proven using deductive reasoning. And once we've proven them, we can use them to prove other theorems. So what do they have that's different? Theorems have to be proven using deductive reasoning. Postulates are assumed to be true without formal proof. Both can be written as a conditional, and both are used in proofs. All right, so we're getting back to that page that had the properties of equality. There's a couple things that we need to talk about, and that's the difference between equality and congruence. Congruent, remember, means equal in measure. So when I say, oh, angle ABC is congruent to angle BCD, yes, they're congruent, but I'm actually saying they're equal in measure. When we write proofs, sometimes we want to talk about things being congruent. So when we get to proving congruent triangles and similar triangles, we're going to want to talk about things being congruent. So then we're going to use properties of congruence. When we're doing some of our proofs, though, we're actually using equations. Some of them involve linear pairs, so things that add to 180. Some of them involve things that are equal, like vertical angles. And so it might be convenient, instead of talking about them being congruent, to talk about them being equal in measure. And so if we want them to be equal in measure, then we would use some of these properties. We'd use a property of equality, POE, versus a property of congruence, POC. Now there are three primary properties that we use in proofs, and you'll see some of them at different points. The top one and the bottom one are especially critical when we do certain proofs. The middle one helps us to flip things around if we don't like the way it's written. So the first one is the reflexive property of equality. This basically says that something is equal to itself. It's like looking in the mirror. A is equal to A, or distance from A to B is equal to the distance from A to B. Or the measure of angle A is equal to the measure of angle A. It says something is equal to itself. So I'm going to make this measure of angle A, measure of angle A. Whereas if we're talking about them being things being congruent, the reflexive property of congruence would say angle A is congruent to angle A. The segment AB is congruent to segment AB, as opposed to saying the distance from A to B is equal to the distance from A to B. It seems a little silly now to say something is congruent to itself, but you'll see why it's so important in some of our future proofs. Symbolic property of equality, or symmetric, not symbolic, symmetric property of equality just turns things around. How many times have you solved an equation and you had 10 equals x, but instead we've said, so x equals 10. In switching the order of the equation, we didn't change the fact that it was equal. So what they do is they say, well, this is called the symmetric property of equality. That's like saying, measure of angle A equals measure of angle B, so the measure of angle B equals the measure of angle A. All we're doing is changing the order of the sentence. And we don't do this a lot. We tend to do it more with algebraic proofs, and sometimes in geometric proofs as well. So if it's saying the exact same thing, only switching the order, it's kind of like the converse, except it's not a conditional. So it's still true, 100% true, either way you write it. We're just switching the order. So for symmetric, it would be saying angle A is congruent to angle B, so angle B is congruent to angle A. All it's doing is switching the order. It says the same darn thing. Transitive property is what I call the train. And this is most like our law of syllogism. It takes a connection of things through equality or through congruence and connects two that may not have been directly connected. So an example of this with just letters. A equals B and B equals C, so A equals C. Well, if A is the same as B and B is the same as C, of course A is the same as C. This is like a train. We have the engine and we have the caboose. It doesn't matter which one. And B is the connector. kind of like the law of syllogism, but it doesn't have to happen in a particular order. So we will see things like AB equals XY and XY equals CD. So AB equals CD. Because we're talking about distances being equal, XY being the connector, this is the start, this is the end, now those are equal, that is the transitive property of equality. If I instead were saying segment AB is congruent to segment XY and segment XY is congruent to segment CD, so segment AB is congruent to segment CD, then I'm talking about them being congruent, and I can see there's the start, there's the end, there's the connector. This again is the transitive property of, this time, of congruence. Take a moment to see if you can figure out which of these properties are at play in letters A through H. So pause the video and see what's at play for these. Welcome back. Letter A, if you guessed, you see the same thing on both sides, so you know it's reflexive, and you see this congruence symbol, so it is the reflexive property of congruence. Number 2, you see angle 1 is equal to 2, so 2 is equal to 1. They're saying the exact same thing, they've just changed the order, and because of equality, it will be a property of equality. It is the symmetric property of equality. Letter C, AB, there should be bars on these. It's not written that way, but it's a congruent statement, so it should be. AB is congruent to CD. CD is the connector. AB and CD is congruent to EF. So here's my start, here's my finish. The conclusion is AB is congruent to EF. This is the choo-choo transitive property of congruence. POC, property of congruence, since we have a congruent symbol. Letter D, saying the same thing on both sides. Something is equal to itself, so this is the reflexive property of equality. Letter E, they've just changed the order, so it is the symmetric property of equality. Letter F, again, reflexive property of equality. Letter G is a little different. There's a couple different things to it. Zeros, or O, I'm not sure, is equal to A, and A is equal to X, so I have a start and finish. 0 is equal to X. This is the transitive. In this case, they're all equals, so it's property of equality. And lastly, they've switched the order, but they're saying the same thing on both sides. It's just switching the order. So it is the symmetric, and this time they're talking about things being congruent, property of congruence. This concludes part of this, but not all of it. This starts the notes for this. I will have some supplemental examples on how to do the proofs in an additional clip, but if you know how to do these as you look at them, or maybe you just want to watch and review, you want to make sure that you know how to do some of the geometric proofs we did last time, or how to set them up at the very least. So I will have some supplemental examples of that in a separate clip, but this is the conclusion for 2-6 for now.